All right, so I'll start number 15 here, and I'll start actually with one thing that I would give you a little bit of I think a helpful hint for chapter 30 is that there are a number of equations that were derived for magnetism using Biot-Savart or Ampere's law, and just to rattle off a few. We had the equation for a wire, and we had the equation for a loop, and we had the equation for, well, then, and I guess special cases of those would be like an infinite wire, and for the loop, I guess a special case would be right at the center of the loop, or another special case would be a fraction of a loop. Trying to think what else falls in this category. Oh, solenoids, toroids. Anyways, all of those were derived. And so if you commit those to memory and know when to use them, that's going to make this chapter straightforward. So an example of that is right here. The magnetic field is mu naught I over 4 pi a, and then we had this sine theta 1 minus sine theta 2, and that was the derivation of the magnetic field if you had this wire carrying a current and left to right, and then there was some point P over here that's a perpendicular distance a away, so that's where the a comes involved. The current is I, and theta 1 would be an angle that is created from this perpendicular distance to the beginning of the current. And theta 2 would be the angle from the perpendicular distance to where the current ends on a straight section. So for this problem, I bring that up because it says here, two long parallel conductors. All right. So if these things are really long, then I would really be drawing a line that's something like this, way out to the beginning. And so this angle of theta 1 is nearly 90 degrees. And this line going to the end, I would draw something like this. And so it too would be 90 degrees, actually, excuse me, negative 90 degrees. And so when you put this into here as 90 degrees and negative 90 degrees, you reduce this to what I call the special case, where you have this infinitely long wire, or at least a very, very long wire. And so it becomes a mu naught I. And if you look, sine of 90 is 1. And sine of minus 90 is minus 1. With that minus in front makes a plus 1. So it's plus 1 and another plus 1. That's plus 2. Canceling a little bit with the 4. So we get a 2 downstairs. And then, of course, we also derive this using Biot-Savart. So the equation for a very long wire is one of these special cases. And that's what I'm going to use here. Okay. Because again, I'll go back to 15 where it says two long parallel conducting currents of I1, which is 3 amps, and I2, which is also 3 amps, are both directed into the page. All right. So keeping that in mind, I'm going to use this equation twice, actually, for the strength of the magnetic field. So if I kind of draw what they have here, and part of this challenge might be more visualizing this in 3 dimensions, but the current would be going into the paper. And so we have this current of 3 amps, but it's going into the paper. And so one of the right-hand rules here is to say, all right, take your right hand and make a little thumbs up. And for things that are straight, use your thumb for the current. And your fingers will give you the field. It also works for currents that are in circles or arcs, where you use your finger for the current, and then your thumb gives you the field. So I think maybe that's one of the challenges of the right-hand rule, that students, say, well, what am I supposed to use for the current? Is it my thumb or my fingers? Well, it's both. It depends on what shape of object you're looking at. So in this case, the shape of the object is a straight line. So I'm going to use my thumb for the current. So if I then put my thumb in the direction of the current, you can see that my fingers then make a clockwise curve. And so the field would be going clockwise for anything going into the paper, okay? So I'll keep these two things together in mind to solve this problem. And I'll start with the field from number one, just the magnitude of it. So it would be mu naught times I over 2 pi, and you can either put an R or an A here. And as we fill this in, this mu naught, the permeability of free space, is 4 pi times 10 to the minus 7. The current is 3 amps. We divide that by 2 pi. And the point P is a distance of 5 centimeters away. And maybe I can even cross out a little bit and get my first number for what is the magnitude of the field from number one. So this is 2 times 10 to the negative 7 times a 3 divided by a 0.05. So we're looking at 1.2 times 10 to the minus 5 Tesla for the strength of the field from number one. Now, doing the same logic for number two, I would put in the mu naught, the I, the 2 pi, and the distance away. So this is the 4 pi times 10 to the negative 7. I believe number two also had 3 amps. Good. Then I can divide by 2 pi. But now we're a distance of 12 centimeters away. So a little bit further, but same basic idea. In fact, I think I'll just go re-enter and back that off to a 12. So there's the 2 times 10 to the minus 7 times the 3 divided by the 0.12. And so this would be a 5 times 10 to the minus 6 Tesla. Okay, so minus 6, minus 5. So smaller field makes sense. We're a little further away. So those are the two magnitudes. Here's where, though, we have to come back and remember that they are vectors. Let me put page 1 here. Because if I then say, okay, let me put current number 1 here, and I'm going to come down 13 centimeters. Current number 2. So here's number 2. I should put an X going in. Here's current number 1. Put an X going in. And we're looking at some point here, which is 5 centimeters away, 12 centimeters away. And I don't know if you remember your magic triangles. They were actually being nice to us to save ourselves a little bit of work. But there are some magic triangles that are at right angles to each other. The 3, 4, 5 right triangle is one of them. That's usually considered the first one. And then the 12 or the 5, 12, 13 is the other one. So this is actually a right angle. That may not be so noticeable to you. And so if you don't remember your perfect triangles, that's understandable. But then you're going to have to go through some work to figure out what that angle is. And so we can, do an inverse tangent and an inverse tangent and law of sines or law of cosines also. Whatever you want to do to get that angle is not, and you're going to come up with 90 degrees. So I'll take the short method, if you will. And here's why that becomes really helpful, because as we came back here on page 1, remember I said this is the formula for the magnitude of the field, and using our right hand is the way to get the direction. So what that would mean is the field from number 1 would be tangential to a circle that is drawn with a radius of 5. And tangential is perpendicular, so that tells me that this field is actually along this direction pointing to number 2. I don't know if that's going to help or not, but that's where that 90 degrees can be kind of useful. Let's see, what does it say? It says determine the magnitude and the direction. So we do have to mess with direction here. Okay. Now, using that same logic, I can do the field from number 2. And so number 2 right here would be a field that is tangential to a circle. The fields would be pointing in a circle out here. And we're interested in the field right here. So the field would be pointing in this direction. So let me call that field number 2. Let me call that field number 1. Okay. And we've got, many different ways we can go from here in terms of what is its direction or what is its magnitude. Maybe the first thing I'll do is just get its magnitude, because I can see, because of this 5, 12, and 13 perfect triangle, that this is 90 degrees. And so this would be like an x-axis and a y-axis. And so when you add an x-axis and a y-axis together, the x squared plus the y squared is the hypotenuse squared. So that's the approach I'm going to take. In fact, maybe in my picture, I should draw number 1 a little bit bigger, because it does have a bigger strength. And if I, wanted to make a grid here, and depends how you want to specify this grid, it says magnitude and direction. And I'm wondering if I should do kind of a grid that's kind of tilted. So this is the x-axis and this is the y-axis. See, once I do that, then again, you can see a lot better that field number 1 is along the y-axis, negative y-axis, and field number 2 is along the x-axis. So when I write here, what is the magnitude of the total? I would say it is the x component squared added to the y component squared. And that just makes it a little easier. If I did a different grid, the traditional grid, then I would have an x and y component of each of them. And that wouldn't be so hard. I would just have to add x's to x's and y's to y's and then do the Pythagorean theorem. But with it twisted like this, I can just apply the Pythagorean theorem right away. So coming back to page 1, I've got the x-axis is 1.2 times 10 to the minus 5, and I'll square that. And the y vector as 5 times 10 to the minus 6. I guess technically negative on my grid, because I haven't put my grid. Field number 2 is, I did those backwards. The x-axis is number 2. There's the x-axis. And the y-axis is the stronger one, number 1, and it's in the negative direction. All right. But again, as you can see, which one you call x and y is kind of irrelevant here. But just so that it matches my grid, and let me be more careful and call the weaker one, the number 2, the x-axis, and give it a positive, and put it here, and the y-axis, the negative one, and then square it so it goes away. All right, so then I can get the magnitude by taking, I guess it would be this last answer, and square it, and add it to that one squared, hit enter, and then take the square root. Oh, well, that was dumb of me too, because that would be a 5, 12, and then the hypotenuse would be 13. So I guess that kind of makes sense. So they set me up for a 5, 12, 13 right triangle. They're at right angles, and so not a surprise that I get a result that the hypotenuse is a 13 times 10 to the minus 6, and the 2 legs are 5 times 10 to the minus 6 and 12 times 10 to the minus 6. So I guess maybe they wanted us to notice that too, and that would have made it that much easier. All right, so if you notice things about the perfect right triangles, this is a lot easier. If you don't, it's still not that bad. You just have to do the x's and the y components here. All right, now they do say what is the direction, okay? And so maybe the thing to do is to kind of take my grid. Let's see, maybe I'll take a pencil here and say, all right, I have something that looks like this, and it would add up like this. And I think we can argue that angles are the same, and so this is vertically straight down. Let's see. We know that this angle here comes from this 5, 12, 13 right triangle. So whatever this angle is, and of course we could actually figure it out. Let me just call it theta. And of course the sine of theta would be the opposite, so 5 over 13. So we could actually get this angle. But I don't think we need to, because I'm going to say that angle is the same theta. And that is, if I wanted to know this, I would go, the angle is the opposite. And so that would be here, which we know to be this 5 over its hypotenuse, which is here, which is the 13. And so it would be the inverse sine of 5 over 13, just like that one would be. And so we would have then these two lines would be parallel, and the transient line that cuts it then is alternate interior angles. So that would be straight down. And so I guess we could just say down, or maybe in the traditional grid, we would call that a negative j hat. And I want to be careful with that. That's the traditional grid down, not the red one that I did. So maybe I'll do a green grid right here. But it's probably better just to say down, straight down. Yeah, that was a little play on angles here. I didn't kind of expect that. In fact, let's see if I can call up the solutions to this. And I'd be curious how much your author did, or did he play with these angles? Let's see. So he does the magnitude of them. Mm-hmm. Clockwise, perpendicular. And he didn't. He didn't really play with these angles. He just stuck to the traditional grid and got the X components of each, the Y components of each, and then added them together, and then eventually got to this 13 times 10 to the minus 6, and in the negative J hat direction. So good. We did it right. A little different than the author.